why don't I introduce you? Great. Well, to start things off, our first speaker is David Wallace, who is the Mellon Professor of Philosophy and History and Philosophy of Science, or just of philosophy.
Kind of the title's kind of weird. I think technically it's Mellon Professor of Philosophy and Mellon Professor of History and Philosophy of Science. That's yeah.
I think there's a Newton's law of failure here.
Exactly.
David will be speaking about learning to write.
Well, since Jim didn't ask for types and abstract, he's given me the opportunity to give a political philosophy talk about appreciation of how democracy works in underrepresented groups. Okay, let me just start by very briefly reprising the sort of main theme of the previous paper of mine I gave that Jim was kind enough to mention earlier. So, basic ideas coming from that paper, though I think not really original in this sense. We have a language-first view of theories, what's often called a syntactic view, on which theories are collections of sentences in an interpreted language. And the relation between theory and world, which I think is the really decisive thing that separates our views of theories, is linguistic. Theories make contact with the world in the way languages make contact with the world, through reference, through truth, through satisfaction. An alternative math-first approach, often that I think unfortunately called a semantic approach. Theories are collections of mathematical models, maybe they're just unstructured sets. More plausibly, particularly in the light of the work of various people in this room, there's some kind of structured mathematical collection, something like a category or similar. But in any case, the theory-world relation is mathematical representation. Is what? The theme of this talk is really how do we make sense of that notion of mathematical representation in a way which achieves the ulterior motives I have in mind for this kind of approach to scientific theorizing, which is to have a picture of the philosophy of science and even more so the metaphysics of physics that's a good fit to the kind of tools we in fact use in physics and doesn't in fact privilege linguistic language-first ways of presenting things. Because there's a fairly clear lacuna in this framework. An awful lot of work is being done by this notion of mathematical representation. A lot is swept under the carpet. And in the paper of mine that Jim referenced, I'm reasonably upfront about that. I say we don't know what mathematical representation is. No one knows what representation is really. No, let's not worry about it. No, move along, nothing to see here, we'll take it as read. So in this talk, I'm going to try to be a bit more substantive about what kind of notion of mathematical representation needs to do the work on a sort of mathematics first view of physics and metaphysics. I should apologize that there are some rough edges here. To some extent, this is work in progress. This is such a good audience to get feedback from it that I thought it was worth sort of pulling the paper forward, rough edges and all. I should also say that I'm going to largely use science and physics synonymously. I'm not really intending a substantive thesis there. There are important open questions, the extent to which the ideas I have in mind here, which are very much motivated by physics, do or do not transfer to other sciences, but just for stylistic variance as much as anything else, I'm probably going to slip between those two at various points. Okay, so here is a very general kind of view from 40,000 feet, schema as to what's going on in representation in a lot of the philosophy literature. It's something like we've got a mathematical model or class of models or whatever, T, represents physical system P if the following things hold. Firstly, T's got some list of features, A, B, C. The mathematical model's got some list of features, A, B, C. The physical system's got some list of features, X, Y, Z. And there's such and such relation holding between A, B, C, and X, Y, Z. And that relation might be understandable purely in terms of features of system doing the representing and the thing being represented, or it might bring in a third-party contribution from the intention of the person doing the representing, or any number of ways of filling in the scheme. But this general scheme you can see running through at least a pretty substantive fraction of the literature on representation. There's a recognized, but perhaps not sufficiently recognized, threat of circularity in accounts of this kind. We can only get that kind of scheme going if we're already able to describe P as having features X, Y, Z. We can only say how that representational relation works, what it is, if we've got a means to describe the features X, Y, Z that the physical system has, by virtue of which is going to be represented by mathematical features A, B, C. We might think of those, we could imagine having a mathematical representation of P in virtue of which we can describe X, Y, Z. But on pain of circularity, it looks like that's not really going to tell us what mathematical representation is. And it looks as if we're going to need some other way to describe P and P's features other than through mathematical representation. And the natural candidate for that tends to be something like description in language, some kind of statement of what the objects are in theory P, what properties they have, which allows us to talk about the features of P and then explain how they're put into some kind of correspondence with the mathematical features of the representing system. And if that's right, then of course, supposedly math-first metaphysics or philosophy of science is, after all, tacitly language first. And that's probably the single most common response I've got to the math-first structural realism paper. And I think it's a real and serious threat for the defender of a sort of math-first style of ontic structural realism. Sort of quick examples how the threat plays out. So a very common way to think about representation is along structuralist lines. T represents P if there's some appropriately structure-preserving map from T to P. And there's enormous literature about just what kind of map that might be. Is it an isomorphism? Is it a partial isomorphism? Is it a homomorphism? Is it something else again? Does it need some further component about our intention to represent? Can it be read off purely from the features of the system? You have a large class of approaches to representation of this kind. But they share an interpretive question, which is, if our structure-preserving map is what's defining representation, well, normally structure-preserving maps, isomorphisms, for instance, are things that hold between mathematical entities. We understand what it is to say that mathematical structure 1 is isomorphic to mathematical structure 2, or category A is categorically equivalent to category B. Prima facie, it's a category mistake to talk about a mathematical structure being isomorphic to something physical. So to get out of the circle and to kind of diffuse the category mistake, we end up needing some non-mathematical way to ascribe a structure. People talk about physical structure to P. And again, the way that's normally done is, despite the supposed non-mathematical layer, set theoretic. It takes the objects in P, it takes the relations they stand in and the properties they have, sort of construed as something we have relatively direct access to, and given to us in linguistic description, and then it constructs from that an isomorphism to the mathematical structure. A different style of representation is the sort of Gricean approach that Cohen and Callender have advocated, which just says, look, T represents P if we intended to represent P, end of story. You know, my cup represents the Big Bang because I say my cup represents the Big Bang. But again, to even get that off the ground, I need to have some way of referring to the Big Bang prior to representing it. And if we want our representations to be just more than gestures, if we want to say, for instance, this collection of partial differential equations represents the motion of the planets in the solar system, and even if that's stipulative, we still need to stipulate that this trajectory represents the motion of Mercury and this trajectory represents the motion of Jupiter. And so we need to be able to talk about the motion of Mercury, the motion of Jupiter, so as to be able to state our stipulated intention. And again, we seem to have that circularity that we escape only by a non-mathematized way of representing the system we want to represent. So, as a warm-up to say why I think this way of setting things up has to be misconceived and there has to be a way out of the circle that doesn't simply privilege our linguistic description, I want to get back to one of the reasons why I think we're driven to a sort of mathematized picture of scientific theories, which is just that we don't, in deep physics, in quantum field theory and general relativity, actually have these supposed non-mathematical descriptions. We have rough and ready heuristics we can say a proton is a particle made of 3 quarks, but these are nothing like fully capturing of the content of the theory. And in fact, if you try to catch them out sharply and precisely, they tend to fall apart around your ears. I think to for something I think I said in the last version of this talk, of this meeting, then the statement the proton is composed of 3 quarks is something between a massive oversimplification in popular science and a story we tell small children. And have those descriptions, it follows that if representation lies in those descriptions, it's opaque to us how we represent. We are unable to state how our representations work. And that's problematic, I think, wherever we are. It's particularly problematic if we think that some aspect of representer's intention is key to understanding what representation is. Because it's difficult, at least for me, to see how I could intend my, for instance, quantum chromodynamic model to represent that which it represents, if there's nothing I can say about that which it represents other than that which is represented by the quantum chromodynamics framework. So I think there's a sort of reason up front to be very worried about the idea that somehow our accounts of representation are going to require this kind of privileging of a linguistic description. But of course, that doesn't get us out of the circle. It doesn't solve the original problem I was raising, that somehow, without doing that, we seem to have no account available of mathematical representation. It doesn't presuppose mathematical representation. Basically, the sort of elevator pitch version of this talk is the circle isn't vicious. And the circle is something we're used to in other contexts. Oh, I should mention in passing, by the way, of course, there's one response one could have to this opacity, which is say, yes, absolutely. Weren't you guys listening? This is why we've been spent the last century complaining about mathematized modern aliens who want to say, well, ever since Galileo, we've lost track of the way in which physics is supposed to connect to the world, or the Bohmians who want to say, without a primitive ontology, how can you possibly understand the content of our theories? Well, these philosophical communities are going to absolutely embrace the conclusion of this objection. But I'm going to assume, for the sake of this talk, a sort of naturalism that says, we have a successful practice in general relativity, a successful practice in quantum field theory, we want to make sense of it. Here's the plan. Basically 3 parts, the main part of the talk. Firstly, I want to point out that language doesn't get a free pass here, that the kind of circularity we're running into is something we see in trying to give theories of language and theories of meaning for language independently of any concerns about mathematics. And essentially, the source of the circularity is something that Socrates told us and Kant reminded us. We just don't have access to the world unmediated. Any route by which we get to the world is always through some kind of or descriptive tool. And so any understanding of content in any of our representation activities, including is going to have to recognize that circle. I'll say more of that as we go on. Second point is, once we understand how language works and the lessons we've learned from theory of meaning and philosophy of language, we can construct accounts of mathematical representation that are non-viciously circular along the same lines. Once we recognize that claim, we don't have good reasons to think that linguistic description is prior to mathematical representation. We find ways to say substantive things about mathematical representation despite the circle, and we're in no worse position when doing so than when we were trying to discuss linguistic representation, that is, theories of meaning for language. I should say it's in the nature of this kind of work that a lot of things being said are things that are being said in other places and other people. So Neil Dewar said quite pretty similar things. Bas van Fraassen, from a much more empiricist starting point, says some somewhat similar things. There's a lot of sort of connections and threads, and as is often the case of philosophy, insofar as there's anything new here, it's just because of putting things together in a certain order. Okay, so let me execute that plan. Step 1. Let's talk about how meaning works in language. Suppose I want to define a given term. So suppose some of you don't know what the word what Los Angeles means. So I give it, or let's say California. So to some extent, I can tell you what California means ostensibly. I can say, look, this is California. It only works if you're fortunate enough to be in California. And even if you are, is this California? Southern California, University of California at Irvine, this room, this bit of this room, the Virgo supercluster of galaxies. Even more extent, which one normally can't, it doesn't anything like succeed in pinning down meaning. Mostly the way we say what words mean is by more words. What's California? It's the largest state in the United States. It's the state in the United States on the western edge of the country. It's the state of the United States in which we're currently standing. We need more words to do it. And in addition to that, the word that are doing it in words is itself imperfect because in many cases words are not fully definable by other words. But the best we can normally do is to give us more words. Which is to say that we don't have a route to say what California means. That doesn't already presuppose a great deal of linguistic fluency. And you see the same thing at the formal level in philosophy of language and theories of meaning. So again, we know quite a lot, but contestedly, we know quite a lot about the various ways in which it might make sense to state theories of meaning for pieces of language. But they're always given again in more language. A classic approach to many theories of meaning takes things like the task T sentences at their core. Our theory of meaning consists of a whole bunch of things along the lines of snow is white, it's true in English, if snow is white. But of course, that only tells you anything if you're already able to understand the right-hand side. Things of this kind are not systematically helpful. You can see if you use a different meta-language from the object language, how there can be substantive content in theories of meaning of this sort. If you just don't speak any German, then being given a sufficient amount of information about the theory of meaning of German in this kind of way is enough to start allowing you to understand German. But you can only do it because you already have a language which is descriptive of those phenomena for which German is being descriptive. So, prima facie at least, there's a problem in trying to say what it would be to understand a language, and that you can't even do it unless you already have an understanding of a language in which to do it. Is that a problem? Well, the positivists thought it was a problem, and they thought they had an answer. You can explain the meaning of words in other words. You can use chains of definitions to say what things mean, but eventually that isn't the immediately accessible. You say what you like about the positivists. They had a very clear rationale for what they were doing. Their verification criterion of meaning wasn't just that they thought somehow it was bad metaphysics to say things that couldn't be verified. It was that they had a positive account, a positive and well-motivated account of what meaning was that required meaning to be given through chains of definitional equivalences that grounded in something immediate and non-linguistic. But for reasons too well known and too extensive to rehearse here, we basically mostly don't think that approach works. Post the kind of collapse of the logical positivist project, what we mostly tend to think now is that we start from the understanding of our language and then we build out. We don't need and we can't get a non-linguistic starting point, but that's okay. Obligatory quote here is Neuref, as Quine quotes Neuref in this context. We're rebuilding our ship on the open sea. We start by understanding a lot of ways of talking about the world and a lot of substantive facts about the world. Taking a lot of that as fixed, we use it to learn more, explain other things, but there was never a point where we could start not having that large amount of understanding. So to illustrate those ideas and show how they're going to connect to how we might learn how theories work, I want to suppose for the moment that something like a language first picture of theories is right, to at least in some domain. And I want to talk about how we come to learn a new language, or a theory stated in a new language, or a new theory stated in a new language. Well-explored problem. Schematized version of the problem is something like, we already have a language, an old theory. We already speak a language and know lots of things about the world in that language. Again, we can't avoid that kind of starting point. That's the lesson of the failure of the positivist project. And now we've got a new theory, and the new theory is again presented linguistically. There's some overlapping vocabulary between the new theory and the old theory, but there's lots of non-overlapping vocabulary between the new theory and the old theory. And we're also just told by the person who wants us to adopt the new theory that there's a bunch of things called bridge principles, such that if we adopted them, we'd be able to derive claims in the new theory, claims in the old theory from the new theory. And then we ask ourselves, what is it to understand the new theory? So, you imagine all the sort of cool kids in the new theory, and they say, coming in, the water's lovely. And we're enthusiastic about it, so we want to learn the new theory. How do we learn the new theory? How do we learn the new language the new theory is written? We can distinguish three answers to this, I think. The positivist answer, I think, is that we don't. We have the framework we have, it's grounded in the given or whatever it is. We've got this new language. The new language is a calculational adjunct to the old language. Insofar as you have a theory of meaning for it, it's a qualitatively different kind of thing. The new theory ultimately just bottoms out in its usefulness as a tool to make claims in the old theory. How we make sense of that, how we talk about it, whether we use semantic language at all to describe it, whether we simply treat it as a black box, whether we say things that look like meaning claims but are thought of as façon de parler. You can do this in lots of different ways, but the sort of shared theme here is the thing we actually understand in itself is still O, N forever and after is just this useful superstructure of it. Here's the second answer, which most famously gets attributed to David Lewis in his How to Define Functional Terms. In very schematic form, we construct a new theory of meaning for N. We learn to understand, we genuinely say what the terms in N mean, but using things we already understand in terms of O. So we are making referential claims, truth-apt claims in N, but the theory of meaning that grounds those, that truth, that reference, is permanently tied to definition equivalence O, such that our understanding of the content then is permanently derivative of our understanding of the content. There's a third answer, I think very explicitly stated by Ted Seiler in his most recent book. I think you can see it in Quine. Arguably, I think you can see it in things Lewis says around the edge of his own presentation. Seiler's answer is, well, Lewis is right to start with. That's how you start to learn a theory. But in due course, you get the hang of the theory, and now you understand it in its own terms. There's a sort of Gestalt shift. And once that Gestalt shift happens, your understanding of N is no longer derivative on O, and we reconstrue our understanding of O in terms of N. So while before the Gestalt shift, we need O as our crutch to understand N. After the Gestalt shift, we understand N in its own terms, and we now re-understand O. Various things Kuhn says about paradigm shifts have something of the same character. Okay, but so claim, that third conception is what one tends to find the nearest reactor of a sort of consensus on how to think about these things in contemporary language and analytic methods. It raises an obvious question, which is recognized. Okay, fine. Those first two accounts weren't just accounts of how we learn a language, they were accounts of what a linguistic meaning was for the new theory. They presupposed the old theory, but they actually told you what meaning claims meant about the new theory in terms of the old theory. If we do this Gestalt shift, if eventually we get the hang of N in its own terms, what is it to understand N? And you can give an internal and external version of an answer to this. The internal, both of which sort of presuppose an understanding in a way. The internal answer, if you like, is what is it to speak the new language? It's to be judged to be using the new language correctly by people who already speak the new language. I'll give you a quick example. Take the English word lachrymose. Who knows that word? Bunch of people, not everyone. What is lachrymose? They want to give me a quick definition of lachrymose? Tearful. Tearful, yeah, that's pretty much what Merriam-Webster says. But it's not quite what it means. You wouldn't say that a 6-week-old baby with colic is lachrymose. You wouldn't say that somebody who works in a restaurant and cuts onions a lot and is quite unusually allergic to onions is lachrymose. That's not to say I could give a better definition of lachrymose. What is it to be using lachrymose correctly? Well, again, dictionaries will kind of help you out by giving you examples of use. I think Merriam-Webster says something like he was lachrymose when drunk or something. But you can't, those definitions are not exhaustive of the content of it. Ultimately, what is, what is it to know what lachrymose means? It's to be using lachrymose in a way such that speakers of English who know what lachrymose means agree that you're using lachrymose correctly. It's difficult to get out of that circle. But one can kind of get out of the circle, and the way one gets out of the circle is through moves of radical interpretation and radical translation. There's an external answer that says, okay, we've got a group of alien anthropologists who don't speak our language at all, who are just studying us as physical systems. And they study our utterances and our scribbles on paper, and they ask, are these humans speaking a language? And if so, what is that language? And their account is going to be something along the lines of, we can correctly understand the behavior of these humans. We can do a good fit to the behavior of these humans on the hypothesis that we interpret them as speaking such and such language with such and such theory of meaning. And that theory of meaning, again, of course, there's a sense in which they got out of a circle, but a sense they haven't. They already need to describe all the things we're doing. And it's that language that they use to state the theory of meaning, which they interpret us as conforming to. Okay, so that concludes my whistle-stop tour of philosophy of language and theories of meaning in the second half of the 20th century. There's obviously an enormous amount to which that's schematic, but I want to claim that line I've just taken us through represents a very mainstream line in how to think about linguistic meaning interpretation in contexts far removed from the philosophy of physics. Okay, so with that in mind, let's think about how we learn theories in physics. I'll run an example. Suppose you've got a student who wants to learn general relativity. What does learning general relativity consist in? Well, I think we can see it goes in steps. So, first step is, no one comes to GR cold. If you've reached the stage in your physics education where you're learning GR, then you already learn a bunch of other bits of physics. You know classical mechanics, you know some electromagnetism, you know some special relativity, you've probably done Newtonian gravity, and a bunch of other stuff. You know a whole bunch about how to use mathematics in various contexts. You know how to represent lots of systems using that. You know how to use electromagnetism to represent laser light. You know how to use Newtonian gravity to represent the solar system. You know how to use it to represent the effect on the perihelion of Mercury or the Jupiter, all this kind of stuff. Actually, to be honest, you probably don't know that one. You should if the course is better designed. These things. How does that work? Deep philosophical problem. If as the student of physics who's got to GR, you don't in fact know how to use the theory that way, then you're being a bit premature trying to learn GR, and you ought to go back and get your head around Newtonian gravity more. It's the start. What one's able to do as a physicist, having learned these things, is to represent those systems in those ways. But GR goes beyond those frameworks. So step one of how you learn GR is that you learn the formal features of GR. You learn what a differentiable manifold is, what a metric tensor is. You learn one of the various of the different mathematical frameworks to set this up. And you also learn some ideas about how you kind of use some of that stuff to represent in ways you already know how to represent. You probably study the Schwarzschild solution and its low curvature approximations and the design calculation, the precession of the perihelion of Mercury. You're able to sort of map a certain piece of GR onto a certain representation you antecedently understand of the solar system and see how that corrects the dynamics while kind of using the kinematics of the Newtonian representation. You solve the wave equation in the weak field limit to look at gravity waves, and you have heuristic grasp of these things from your understanding of it in electromagnetic radiation. You only know a bunch of heuristics. Maybe you talk a bit about jets are curved and how the nearest analog to a straight line is a geodesic on those surfaces, and you look at the mathematical analogies there. Then you get confused and you think that the general relativity says space is curved, and you look at balls rolling on rubber sheets, and it takes you some significant time to unlearn that and realize that space-time curvature is not space curvature, but maybe it helps you out of it. You go through this kind of process. But eventually, that stops being the case. You reach a point eventually where you have a sufficient faculty of general relativity that you know how to use GR to represent rather more directly. You're using GR in a bunch of contexts that are outside the descriptive scope of things like Newtonian gravity. You can study colliding black holes. You can study early universe cosmology. You could see the limitations of those mappings between frameworks, even kinematically. You can see how the inspiraling is not really caught at all in a test bodies on a Schwarzschild description and doesn't really map naturally to anything Newtonian. You understand the idea of gravitational degrees of freedom. You realize the limitations of the weak field limit. And there comes a point where you just want to say, yeah, you understand general relativity. And now those various things that were essential in learning it are crutches that you're no longer relying on. And you're now reconstruing your understanding of Newtonian gravity through its relation to general relativity. And what is it to learn general relativity in that way? What makes it true that you know general relativity? Well, by close parallel to the linguistic answer, we've got an internal and external answer. The internal answer is to know, you know general relativity if you're judged to know general relativity by the community of people who know general relativity. There's an externalist answer, which if you bring in a bunch of alien physicists who also like anthropology as a side hobby, and they want to study what you're doing as a community, you and the other physicists, they, of course, they have great physics and they know how to represent the various situations we represent using general relativity. And they hypothesize, they play the game of radical interpretation. They hypothesize a partial isomorphism or similar thing from the mathematical structures that we say we're using into the mathematical structures they use to represent those systems. And they say on that hypothesis, what humans are doing kind of makes sense. And it makes sense better than other things. And that's what it is for the humans to understand, for humans to be using this theory and for this theory to be representing in this way. Let me fill in some details of this. So I'll give this a name just to be convenient to refer to. We call this a TT account of representation, where TT stands for theories and theorizing. And again, anyone who knows 20th century philosophy of language will catch the reference, but I'll bring it up in a moment. So on this account, you've got two halves. So firstly, we have a story to tell about what an interpreted physical theory is. Like for the aliens, what's the thing that they're ascribing to humans? And we have a separate story about what makes it true that a given community is using a certain theory interpreted in a certain way. So what is it for what is a given theory on this basis? Well, given a class of systems that the theory is reportedly about, and given that that system is represented by some mathematical structure S, then what a theory is an ordered pair. It's a mathematical structure, and then it's an appropriate, fill in the details, serving map from M into the mathematical structure that we presuppose represents the class of systems. So in a sense, you have something like a structuralist isomorphism account, but critically, we can only state the account if we already possess the ability to represent the system by another mathematical structure already. Which is exactly, again, the same circularity we come back to again and again. You can't explain how a representation works unless you're already able to. And then what makes it true that a community is using a theory M, rho, or if you like, what makes it true that a theory is using M to represent by rho, is simply radical interpretation. It's the fact that that's understanding of what the... The reference, of course, is to David Lewis's influential Languages and Language. Lewis says there are two aspects of language that are distinct but compatible. There are languages understood as a formal system, a lexicon, a syntax, plus a mapping from the language into the objects and properties of the world that can be understood as a formal system without any concept of what it is for it to be true that a community is using that language. Then there's separately language, that community activity, that way in which we use language to communicate and refer to things that we intend to refer to. And Lewis's synthesis of this is to say what makes it true that a community is speaking a certain language is the validity of the radical interpretation move that says we make sense of speaking that language than through any other such hypothesis. Lewis in the paper advances specific theories but both as to how the theory of meaning works for a language and how to fill in makes best sense of. But I want to step back a bit from that. The general schema that Lewis presents is prior to the specifics of how we fill in both the formal content of linguistic meaning and the interpretational content of the radical interpretation. Okay, so I'm doing better for time than I expected, so there should be plenty of time for discussion. We got to summing up so far. We recognised the circularity. We recognised that accounts of representation presuppose representation. We saw the threat to ontic structural realism, to a math-first conception of representation, that comes from the idea that the way out of the circle is that we need to presuppose a non-mathematical representation, such as that given in a linguistic description, and then use that to ground our mathematical representation. But we reminded ourselves that that circularity occurs in trying to put together theories of meaning even for language, because we can't say what a language means without already having a language adequate to describe that which the language aims to describe. We saw in various ways how we make our peace with that circularity and are still able to say substantive things about linguistic meaning, do scientific things about linguistic meaning, despite that. We then saw, I claimed for an example, that if we go to a scientific case and we're able to help ourselves to those same resources, we have an extremely similar story to tell about how mathematical representation can be understood non-viciously in terms of antecedent mathematical representation, both in terms in how we learn new theories and externally as to what the truth makers are for the claim that we're using theories in certain ways and using them to represent in certain ways. But of course, that doesn't in itself remove the rival position, if you like. It doesn't remove the position that says, nonetheless, notwithstanding what you just said, the right way to think about mathematical representation is to start with a prior notion of linguistic description and then build mathematical representation on top of it. And for the last part of the talk, I want to talk about that in its own terms, and partly through reference to what's gone before, but partly not, talk about why I don't think that is a good rival for trying to understand representation. So, if you like, here's the target view. Call it language-first representationalism. The language-first representationalist has something like the following views. First of all, we describe the world in language. We understand it in terms of objects, properties, and relations. It's true that how we learn languages, how we learn to apply them, how we learn to extend our vocabulary, that's subtle, it's difficult. Linguists need to think about it, philosophers of language need to think about it, metaphysicians need to think about it. But consider it solved, ex hypothesis, before we discuss the different question of how mathematical representation works. And if it's solved, then we have the substantive resources to directly describe a physical system, and so consider that substantive question about how a system can be represented by a mathematical model. Claim that something like this is tacit in a very large fraction of the literature on scientific representation. It's quite difficult to find an explicit statement of it. It tends to just be taken as read. But historiographically, I struggle to make sense of a lot of what's said about representation without seeing something like this as a reference. So I want to sort of ask, what kind of reasons could we give for thinking that this is the right way to think about representation? I don't think it's the right way to think about representation, and as I say, it's more tacit than explicit, so this is my own attempt to reconstruct reasons of that kind, and the list may be non-exhaustive. And I think trying to think of what the positive case for this is a good, if you like, weak point for critics of the kind of project I'm doing to sort of use and see how their alternative would go. But here's some things that come naturally to mind, to me at least. So the first we've sort of discussed, you might think, well, look, this is the only way to give a non-circular account of scientific representation. But the first part of the talk, I've tried to establish that that doesn't seem to be the case. The circularity we have in mathematical representation is vicious. In any case, it recurs in theory of linguistic meaning mutatis mutandis. So if we don't like that circularity, we don't avoid having to have it just by privileging linguistic representation. The thing you get, I had this in conversation, is something like it's beyond our cognitive capability to understand the world except through a linguistic description. Reply to that response is, well, I mean, I'm sorry, it's beyond your cognitive capacity. These theories this way. So do plenty of other people. Are they mistaken? Are they lying? One would have to give some positive account of that kind. It's question begging to suppose that if somebody is saying, I can't understand it, you have to explain this to me in these terms, that it should automatically be assumed there's a way of explaining it to them in those terms. I mean, Tim Maudlin, ironically, has this kind of comment in a paper of his about probability that I meant to look up before slides and didn't have a chance, where he's trying to talk about probability as being a primitive notion, and he says, well, what about the person who says, I don't understand what probability is? And Maudlin basically says, that's your problem. He quotes Berkeley as saying something like, sir, I am obliged to give you an explanation, I'm not obliged to give you an understanding. The other slightly more conciliatory thing to say is, well, maybe there are cognitive limitations on humans to do with our nature as physical systems. I mean, there are even some theoretical arguments, things like Froede's language of thought, that might push you in that kind of direction. But insofar as these are cognitive limitations on humans, then there's a certain somewhat Pyrrhic victory there for a language-first approach, because that would just be to say something about humans, not something about what the world is like in itself. But also, I think more importantly, the only way to establish that you have a cognitive limitation that blocks you from understanding something is to work really, really hard to understand it. You can't saying I am cognitively incapable of understanding this thing, therefore I get out of the really hard work of working sustainably to try to understand it this way. It's kind of like the equivalent of saying I can't do math. in a sense, perhaps it is. Here's a third, and I think more interesting argument, and this actually is again something in conversation I've had very extensively as feedback on my earlier paper on this. Something like, well, here's the difference between the linguistic representations and the other forms. Our pre-theoretic understanding of the world is language first. That's how we grasp the world as children, it's how we grasp the world prior to being theorists. This mathematical representation is a new concept, an alien concept. Maybe it turned up in the Renaissance, maybe whatever. It demands explication in terms of the difference comes from the difference between this new and alien thing and this older and more familiar. So two thoughts in response to that. I mean, one is it's not clear why the demand should actually be met. I mean, stipulate that it's true that our representational tools be scientifically or all of a certain kind. That's still a limitation of ours that we might want to transcend. And this takes us back a little bit to the cognitive capability concerns. I mean, if it's the case, our existing representational tools are obviously evolved and adapted for the context in which we find ourselves. It's extremely plausible that they're limited and not optimal in describing things well outside our kind of evolutionary and cultural niches prior to modern physics. But if that's true, that seems to be all the more reason that we want to sort of see if we can find ways to learn how to learn and understand other representation schemes. But more importantly, and this is my last substantive point, I don't think this claim about our pre-theoretic understanding is true. I think long before you start learning formal science, a huge aspect of our representational practice is mathematical and not well captured as purely linguistic. And I mean, just before I take through in a bit more detail, I want to say that position is profoundly unoriginal and widely recognized in other places. I mean, if you want to ask when did people first start saying that we had kind of an innate understanding of mathematical concepts, Well, the first time I know it turning up in the Western philosophical tradition is in the Meno. Socrates' whole point, as I attempt briefly here to bluff ancient philosophy well out of my depth. But my reading of Meno is that the person to whom Socrates is teaching mathematics is somebody who is being encouraged to remember and re-grasp their pre-given innate understanding. So Socrates reconceptualizes this in terms of remembering past lives, but what's really doing the work there is that his interlocutor's understanding of the mathematics is innate. It's not something that's being learned as a superstructure over a prior non-mathematical description. The central role for the intuitions of time and space in Kant's philosophy seem to play very much the same kind of role. But to go from a more sort of contemporary perspective, so if you think about our human perceptions of these things, ask of how to think about and represent objects in space. We know how to use spatial ideas and spatial locutions and spatial ways of thinking in a routine fashion. We know, as Kant didn't, that there are ways to provide a linguistic formulation of the assumptions that go into, say, Euclidean geometry. But that's a very hard-won mathematical achievement that took thousands of years to get. It can't plausibly be said to be our explicitly understood, direct understanding of what geometry is. Similarly, representation of process and time, again, in Kant's other case. You might also think about comparatives. Think about, this thing is twice as heavy as this thing is twice as long as this thing, took twice as long to get from here to there. Some of these are spatiotemporal, some are not. Even qualitative comparatives, like he's nicer than he is. If you're a first-year logic student, you run into these things as two-place relations. You quickly discover that, of course, the formal rules of logic don't capture things that you intuitively know to be true about these things. You start learning how to write down assumptions that do capture them. So you learn how to define a relation as irreflexive and asymmetric and transitive and what have you. What you're doing really there is capturing your prior understanding of the nature of these comparatives as giving an ordering relation. If you try to do those kind of games for quantitative comparisons like length or mass, it becomes something of a nightmare. There's a burgeoning literature on comparatives in metaphysics of physics. And in that literature, you'll find things like formalizations of comparatives that posit a continuum infinity of mass properties and posit a whole bunch of axioms governing the two-place relations between mass properties and massive things. And these axioms are obviously built to reverse engineer the fact that the mathematical structure that represents mass is something like half of a one-dimensional vector space. Whatever the values or vices of those projects of metaphysics, they're not at all plausible as conceptual analysis of what we pre-theoretically understand mass to be. Or as a final example, think about fluids and continua. We routinely describe, we understand the notions of things like fluids having certain densities that vary smoothly across them, temperatures and velocities that vary smoothly across them. These are quite subtle notions to mathematically formalize and extremely difficult. I don't even know if solved to throw into a first order linguistic formalism. But we understand them from a very early age. So my 3-year-old daughter, if you ask what her mathematical understanding, what her explicit mathematical understanding is, the way she counts goes up straightforwardly as far as about 12, skips 13, continues up to about 17, and then gets to a loop where she goes back to 12. She has a perfectly clear grasp of statements like the water at that end of the bath is hotter than the water at this end of the bath, which, if you ask how to represent that, ends up being something about real functions on a three-dimensional manifold of a kind that's clearly ridiculous beyond. I want to claim that this kind of the way we represent generally is just infused with mathematical notions, and it's just false that prior to doing modern physics, all of our representation is well captured in the sort of normative sort of logic or anything similar to that. And I think you can see that also from some more external point of view. If you ask what does radical interpretation of humans look like, if you looked at human, pre-scientific humans even, behavior, then I think the natural presupposition is that radical interpretation would ascribe humans a whole bunch of representational capacities distinct from, although in various places overlapping with, their linguistic representational capacities. And if you ask this as sort of a more, if you don't like the sort of quasi-behaviorist, externalist way I've been talking about a lot of mental states and linguistic states, neurologically and evolutionarily extremely implausible that all of our representational capacities are grounded in our linguistic representation. Apart from anything else, combinatorial semantics is an extremely unusual evolutionary achievement that plausibly only humans have got, and yet vast numbers of animals are capable of handling and engaging with space in ways that it's completely normal in zoology and ethology and cognitive science to explain in representational talk. Okay, let me wrap up. So, conclusions. It is impossible to state how a mathematical model represents a physical system, and you're already able to represent that same system. But that's okay. That's not a vicious circularity. That's something we've all faced in philosophy. It doesn't prevent us saying substantive things about what mathematical representation is, and it occurs in linguistic representation, extremely similar. And so there's no good case for mathematical representation is fundamentally derivative of representation in natural language. Or at least if there is a good case, I have yet to see it. Thank you.
Okay, I'll chair.
Maybe the most philosophical talk. No questions.
Yeah, so on that previous slide when you're talking about these pre-linguistic mathematical representations, so I like all of this, I like all these examples, except I'm not convinced that it's right to think of them as mathematical representations that are pre-linguistic.
Okay.
I mean, the way I'm almost thinking about this is that maybe you have a mathematics third view and language is second, and there's some other, that there are all sorts of innate representational systems that we have, and like Fodor thought we could explain all this in terms of language, and you're maybe saying maybe we can explain all this in terms of mathematics, and I think language and mathematics are capable of discussing these things. And I think you're completely right that once you've absorbed one of these newer representation systems, I mean, when I say mathematics third, I don't mean like ontologically third, I just mean temporally third here. And so I'm wondering how important is it to you that these pre-linguistic things are actually mathematical rather than just saying they're different from linguistic representation, and maybe they're as different from linguistic representation as mathematical representation is, but do they have to be understood as mathematical representations, or is it okay if we just think we have some variety of representational capacities at different types of life stages, and when you learn a new one, it can become your primary one if it's more effective, you find it more effective in like the Kuhnian sort of way.
Yeah, I'm not 100% sure of the right answer to that. And I think to some extent it might be a semantic matter. I mean, I'm not necessarily committed to whether we want to say our spatio-temporal representation is mathematical. I want to give the externalist description of our spatio-temporal representation. We do it most naturally mathematically rather than in a first order logic kind of framework. So in that sense, insofar as we're doing scientific theories of these representation capacities, I think they're mathematical. But that doesn't necessarily mean the right thing to say from the inside out is that they're mathematical. But that said, I'd probably say, I think once you accept the sort of mathematics first conception of what physics theory is like, then you start reconstruing the linguistic theories as sort of special cases.
Yes.
And so in that sense, I treat sort of mathematics as quite sweeping here. And I think if you look, having tried to bluff Socrates a minute ago, I'll try to bluff Kant. I mean, I think if you look at the way Kant talks about our kind of our sort of conceptual grasp of space, then in one sense that's mathematical is the starting point. But in another sense, of course, it is precisely mathematical, and to some extent it's intimately linked to what we mean mathematically. So that sort of gets back to my thought that it might be almost a definitional matter by way to say this is mathematical.
Emily?
Yeah, thank you. I guess it's sort of just anecdotally, it sort of seems that different people approach doing maths in different ways. And so in particular, I've noticed there's sort of a broad class of people who tend to do maths by translating it back into language and like talking themselves through it linguistically. And then there's another class of people who seem to think directly in terms of maths and don't affect that kind of translation. I guess I wonder, how would you see those individual differences as fitting into this story about mathematical representation? Like, do the translators have a lower level of understanding, or they're not doing it right, or are those like equally valid ways of interpreting maths?
Okay, so there's a bunch of thoughts about that. It's interesting. So one thought is that the way people do maths qua math is something I haven't really commented on or thought particularly deeply about. I'm concerned pretty much exclusively here with how the mathematics relates to the physical goings on. In that context, I think the thing about the sort of descriptions in language is they're not, going back to the sort of thing in my previous paper, that I don't think those can really be understood as full translations. They're sort of partial, sometimes slightly heuristic descriptions. I think they do quite a lot of work. I don't want to underplay the significant cognitive significance and the pedagogical interpretive significance of our various linguistic overlays onto mathematized scientific theories, but I think those can't really be understood as the last word in how people think about it. And you can kind of see that in the fact that if you're actually doing theoretical physics, a verbal argument for P that just can't be related to mathematical framework doesn't trump a mathematical argument for not P. The only other thing I'd say on that is that I think, as a very different kind of quasi-psychological matter, I'm fairly suspicious of the veracity of people's accounts of their internal reasoning process when they're doing mathematics, or really any cognitive thing. What one's internal sense of the narrative one tells oneself while doing it may be anything from completely central to the cognitive task to totally epiphenomenic to it.
Okay, Carrie.
Thank you. I love this. I just want to say this is just a comment and something that I'm looking at right now or trying to educate myself on. So these worries that it's beyond our cognitive capacity to understand the world through anything other than a linguistic representation. This is so you disagree. You say you disagree with this, but this worry is there right from the very beginning of the project of the mathematicalization of nature, right? And it's something that Galileo writes about a lot. So he's got his two books, right? The Book of Nature that's written in mathematical characters, and you have the Book of Scripture. And they are incompatible with one another, it seems. So this is something he writes about in Copernican letters, for example. And obviously, I guess, so he says, this isn't the most famous version of the quote, but the Book of Philosophy, the Book of Nature is that which stands perpetually open before our eyes, but it's being written in characters different from those of our alphabet. It cannot be read by everybody. And the characters of this book are triangles, squares, circles, spheres, cones, pyramids, and other mathematical figures, the most suitable for that sort of reading. Similarly, just to quote one more, Holy Scripture and nature derive equally from the Godhead. To accommodate the understanding of common people, it's appropriate for Scripture to say many things that are different in appearance in regard to the literal meanings of words from the absolute truth, right? On the other hand, nature is inexorable and immutable, never violates the laws imposed upon her, and does not care whether or not her recondite reasons and ways of operating are disclosed to human understanding, right? So he's got this whole theory that, yes, when you have the myth of the miracle of Joshua and the sun being held still so that the Israelites can go to safety before night falls, he's saying that this isn't incompatible with the Book of Nature. It's God has a reason to sort of to put it in language which necessarily distorts what's going on in the underlying nature, because he has to make it accessible to the scientific kind of laity. So, we have a whole story that can talk about physics practice and we can talk about evolution, but I just want to make the point that worry that there's there are two books, there's two sets of languages, one is better, the other one we have to make something accessible or has performed some other function tied to our limitations, but that distorts the underlying mathematics, is right back at that rehearsal, the moment when everything starts going wrong, right back at the very beginning. And it just is a little HPS spin on this.
Good, that's really helpful, that's interesting. I mean, the only thing I say to that is, well, kind of relating a bit back to my worries about our supposed innocence of mathematics. I mean, I think I absolutely see there's a substantive problem that comes, can we understand the much more mathematized way in which people like Galileo are trying to do physics as compared to the way we were understanding things previously. But I don't entirely want to annex that to a maths versus language framework, because respectable amount of how we understanding things previously was still in geometry. So, and again, somebody who understood Kant fast enough, they'd probably be able to make the right historical connection. In lieu of that, I mean, I'm just going to say there are obviously sort of geometric things. There are circles in the Bible.
Right.
The Gospel of John, though, of course, is a language first view.
Daniel.
Yeah, great talk. Thank you very much. And apologies for the potentially naive question, but can't you simply resolve the conflict between math and language just by promoting math to be a language or demoting it, however you describe it? You know, we accept that some languages are better describing things than others, right? You know, some things culturally crisp in one language are very clumsy in another. Can't we just see math as a new kind of language that very precisely describes the theories in a very natural way, and then explore the structure of that mathematical language as a way of learning about the world, the way you might like explore the structure of teenage slang to understand, you know, what are teenagers really thinking?
So there's a shallow sense which I think that's fine, but if it tries to become substantive, I think it doesn't work. I think, and here's the point I mean: if we want to just say language is now our phrase for any representational tool we like, then that's fine. If I want to say, look, if I draw a map on board of how to get from here to some pizza restaurant, and you say, so you've used the language of maps to tell me how to get to the pizza restaurant, that's totally fine. Or if if you ask how did somebody's day go, and I roll my eyes, and you say I'm communicating using the language of rolling your eyes. But I think there's a really important narrower sense of language in which language is a much more specific representational tool, which has a compositional semantics, which has a substantive notions of reference and truth, which has lexicons and grammars and this kind of thing. At that point, it stops being true that maths is a language any more than maths is a language. And I think a large amount of our representational discourse and philosophical discourse, this kind of assumes language in that somewhat narrower sense. So if one, for instance, if one asks, okay, what exists according to this language? Well, that's a coherent question to ask if we use language in the narrow sense, because languages have quantifiers, and you can tell Quinean stories about what they quantify over. But that kind of what exists question is not askable straightforwardly if one's representational tool is not a combinatorial semantics with a bunch of quantifiers in.
So we have 1 minute left. Neil is next on the queue, but I want to invite JB to come up and start setting up while Neil asks.
This kind of ties in really actually to what you were just saying. So I'm wondering about kind of another argument for linguistic representation or language first representationalism, which would be stressing kind of the communicative aspects of language. So I'm wondering, I'm not sure if I buy this, but I'm imagining somebody who says, look, even in the Mino, she like draws the circle on the ground and whatever else happens. I think I know even less about the Mino than you do. There's then an argument, like he gives an argument, he walks the slave boy through a proof. And that's something that happens in language, and perhaps this is maybe the trickier part, and would be has to happen in language. Yes, that language requires it. So then, for that communicative or subjective aspect, you need language.
Yeah, no, I think there's something in there. I mean, notice that I gave a talk in language. Even theoretical physics talks are given in language. and even, textbooks of the most abstruse mathematics you like are written in, extremely formalized and technical, but still in natural language. So I think there is a sense in which there are certain communicative capacities that we have that do seem to be unavoidably tied to language. And I'm not 100% sure what to say about that. I mean, that's a place where I genuinely would feel quite tempted to say, well, that's a genuine cognitive feature of humans. That aspects of how we cognize and communicate are linguistically tied there. But I don't think it needs to follow from that our sort of first-order representational tools need to be thought of as themselves linguistic, even though we aren't fully able to communicate and reason without them. I mean, I'm slightly thinking aloud, that's my...
Okay, join me in thanking David.